Hi, my name is John. This is part two. I've got to do a couple more examples as well as types of non-differentiability. So chapter three, section 2 is called the derivative. This is actually starting on page 180 of Anton. So if you want to change your text to page 180 of the function f of x equals square root of x, chapter, excuse me, example 4, we're going to find the derivative and the slope tangent at x equals 9 for part B. Okay, just listen and watch the show because all of the information are given on the example. Well, first of all, the function f of f prime of x by definition is the limit as h approaches 0, f of x plus h minus f of x all over h. You notice that I'm going to draw this out first. Make sure you get your basic functions. This is the parent function. Y equals the square root of x, right? As x is 1, my y value is 1. Square root of 1 is 1. At x equals 4, which is a little bit higher to the right, square root of 4 is 2. It goes up here. At 9, it's going to go up to 3. So you see how it's kind of like a sideways parabola. Of course, this one would be y equals negative square root of x. Okay, so it is a parabola if you look at the bottom portion as well. But anyways, so looking at the top portion, we have to figure out what x is, f of x plus h, excuse me, would be. You plug it into this, it becomes the square root of wherever there's an x, we replace it with x plus h. And there it is right there. So by definition, f prime of x is equal to the limit as h approaches 0 of square root of x plus h minus f of x, which is this right here, replaced with square root of x all over h. You have a problem here because we have a kind of like a complex information set. So the trick, I'm gonna use red right here because this is the key. Okay. Key, what do keys do? They open the doors to knowledge. So this is the key. You're going to multiply the top and bottom by its conjugate. The conjugate of square root of x plus h minus square root of x is square root of x plus h plus the square root of x. Remember, the signs change here and here. That's all it does. That's why it's called conjugate. They don't tell you in the book that you multiply by the conjugate. X plus h plus the square root of x. So what you notice is when you distribute this out, when you fold this out, this is where the algebra gets a little bit more tedious. Square root of x plus h times the square root of x plus h, since they're inverse operation, the square and the square root cancel, you end up with x plus h. If you notice this times this, the outer portion will cancel with the inner portion. Okay, that's why in conjugates, the outer and the inner always cancels. And then minus square root of x times square root of x is square root of x times the square root of x, which is the same thing as square root of x squared, which is the same thing as get rid of that square in the square root, which is just x minus x all over. And you notice I kept it factored, not multiply the denominator out. Square root of x plus h times, plus the square root of x. Okay. And if you notice, just like I said earlier, the square root of x, x will, a lot of things will cancel with the numerator. And you also notice that, I'm going to use pink, the h will cancel in the denominator, turns into 1 and turns into 1. So you end up with the limit as h approaches 0 of 1 over, the h is canceled, square root of x plus h plus the square root of x. Okay. And what you notice now, you can plug in 0 in here for your h. X plus 0 is just x, right? Within the radical. So you end up with 1 over square root of x plus the square root of x, which is just 1 over 2 square root of x. That was the using the definition. Let's try to use the power rule, if you remember the power rule. f of x is equal to x to the 1/2 power. To go from radical state to an exponential state, remember the 2 right here, that's the square root that goes to the denominator of the exponential state. So you have to be very familiar going from a radical state to an exponential state. Okay, so this is the same thing as that. If you need to brush up on exponential state to radical state, consult YouTube, and there's lots of videos on that. Okay, and so when you take the derivative, f prime of x, we bring the power on down. It becomes 1/2, and then subtract 1 from there. So 1/2 minus 1 is times x to the negative 1/2. How to get rid of this negative on the exponent? You just put it on the denominator. So that becomes 1 over 2 times x to the 1/2. Since we started off in a radical state, we want to probably end in a radical state. X to the 1/2 is 1 over 2. X to the 1/2 is square root of x. And there it is. There's your answer, okay? So the key is multiplying by the conjugate so that you get rid of some of the, and a lot of times you'll either multiply by the conjugate or multiply by the LCD with the numerator and denominator, okay? That's part 1. Part 2, now you add the slope at x equals 9, you just plug it in. 1 over 2 times the square root of 9. Square root of 9 is 3, times 2 is 6. And there's your equation for your slope. The slope is 1/6. At approximately 9, the slope is going to be very flat, kind of like this, okay, at x equals 9. And that's your first part 1, which is f prime of x, and part 2 is find the slope at x equals 9, 1/6, okay. The second part is pretty simple. It tells the derivative is what kind of derivative? Non-differentiability. Non, where you are not able to take the derivative. So something like this is at point C right there. As you see the slopes coming here and here closer, it seems to be like the slope is this way. As you're going from the right, and the tangential slope seems to be going this way. So is it this portion or is it this portion? You can't have both. So as a result, it's non-differentiable. They call this cusp. I believe this book calls it a corner. Okay. The second type of non-differentiability is if you have something like this. At this point, C right there, the slope seems to be right here like this, tangential slope, and then you hit it right here and you go, wow, that's a vertical slope right there, right? And then you go to the right, and then it goes to, here's your slope, your tangential slope. So it starts off at slope right here, and it goes to a vertical slope, which is undefined. Vertical lines are undefined, and then you start going to the right. Okay, so that's how you work this out. So it's non-differentiability at a vertical line. The third type of non-differentiability is you have what's called a jump discontinuity. Okay, and so let's get point C from the left. That's your slope right here. It's going to be more positive. As you go from the right, you notice that the slope is going more negative. So slope here from the left, it's going to be something like this. And the slope from the right is going to be something like this. So when you have a jump discontinuity, you're going to probably have non-differentiability, or you are not able to take the derivative. Okay, they call this jump discontinuity. I'm going to say something about one other thing. So, what if you have something like this, where you have an open circle? This is a type of discontinuity, but is it differentiable here at point C? Well, from the left, as you can see, it's going this way, and so you end up with this slope. as you go from the right, using my marker right over here, you're going, here's your slope, and you're going towards the same slope. So therefore, this is called a point discontinuity, and you are able to take the derivative at a point discontinuity, but not at a jump discontinuity. Okay? Good luck on your homework, guys, and hope you enjoyed the show.